Well, hello, everybody. Happy Friday to you. The end of another great week of distance learning, right? Today, we're going to finish up with hyperbolas. We're going to finish up with the last topic of the semester. And then we will have next week to get you guys ready for the test that will be 1 week from today on Friday. So here we go. I just have a few examples for us to take a look at today. I'm actually not going to teach you anything today, just go through examples and reinforce the stuff that we learned yesterday. So actually, if you're fine with yesterday and everything makes perfect sense and hyperbolas are going great, then you could probably go ahead and skip this video and get straight to work. Otherwise, here are a couple of examples of hyperbolas. The first one I want to take a look at is if I give you an equation as shown here, y minus 4 squared over 9 minus x plus 3 squared over 25 equals 1. How do we go about finding the different significant properties, and then, of course, drawing the graph? So starting with the center of this hyperbola, we know that unlike ellipses, the x and y terms can come in different orders. So we have to be careful about this. The x term, I've got x plus 3. That's the same as x minus negative 3. So the x coordinate is negative 3. And here I've got y minus 4. And so my center is at negative 3, comma 4 right there. To find vertices and covertices, I'm going to start with the vertices. Because the y term is the one that's listed first, y minus 4 squared over 9, the denominator is a squared. And so if a squared is 9, then a is 3, which means because we're looking at the y term, we're going to move up 3 spots and down 3 spots from the center to find the two vertices. In this case, we've got them at negative 3, comma, let's see, 4 plus 3 is 7, or negative 3 and 4 minus 3 is 1. So negative 3, 7 and negative 3, 1 are my two vertices. And then to find the covertices, we look at the x term in this case. 25 is 5 squared, so my covertices are going to be 5 spaces to the right and 5 spaces to the left of my center. And so if I want those coordinates, let's see, it looks like the one on the right is 2 comma 4 over 2 up 4, and the one on the left is negative 8 comma 4. The x coordinate of the center has been either increased by 5 or decreased by 5 to find those. Then to figure out the exact shape, well, maybe I shouldn't say the exact shape, but a closer approximation of what the shape is, I close off the rectangle. I've got this rectangle of values here defined by my vertices and covertices. And then I'm going to draw the asymptote that goes through my vertices, or sorry, excuse me, the corners of the rectangle. And actually, I'm going to skip ahead to my next slide because I've got the rest of it drawn out. And then because the y term is the one that comes first, I know that this is going to be a hyperbola that opens up and down instead of left and right. These are my vertices, and so those are actually points that are on the hyperbola. And so horizontal tangent line as it goes through that point and then gradually approaches the behavior of the asymptotes as we get farther and farther away. So there we go. I think I've talked about everything I need to talk about with that one. So let's take a look at a couple others. I want to write an equation ultimately given information about the graph. Be careful on these questions. Make sure that what we're looking at is what we're actually representing on the graph. On this second one, I've got the center and one of each of the vertices and covertices. On the one on the left, I've got the location of both the vertices and the covertices. So let's just take a look at this and see what happens. Let's see, let's put the vertex. I've got one at negative 2 comma 6 and at 4 comma 6. By the way, this also tells me that the center, even though I wasn't given it, it must be halfway in between the two vertices. And same for the covertices. One is at 1, 3, and the other is at 1 comma 9, which is way up there. And so oops, I should finish drawing the rest of that rectangle, or at least the corners of the rectangle, so I know where to draw my asymptotes. I'll have to fix that one just a little bit. So the asymptotes are going to look something about like that. The vertices were these two, the ones that are on the sides, and that tells me a little bit something about what it's going to look like. And so the rest of this graph will look something like this, approaching those asymptotes, and going through the other vertex, approaching those asymptotes. And so now as I come up with an equation for this hyperbola, I will use a whole bunch of information that I just found, starting with the center. The location of the center is at 1, 6. This is opening to the left and right, which means my x term is going to come first. So x minus the x coordinate of the center, x minus 1 squared. And then the y term, let's see, the y coordinate of the center was 6, so y minus 6 squared over something equals 1. And then from the center to get to the vertices, I'm moving over 3. 3 squared is 9, so the denominator of the first term is 9. And then from the center, either to the bottom or to the top, to my code of vertices, we're going 1, 2, 3. Oh, we're going the same thing there. So that'll be over 9 as well. And so there we go. That's the equation for that hyperbola. And by the way, I'll again remind you that you can always go to Desmos and plug these things in, plug these equations in as is, and you should be able to verify that the hyperbolas that you are drawing is actually matching up with your equation. And then the final example for today, my center is given at negative 5, 2. Did I count right? 1, 2, 3, 4, 5. One vertex is at negative 5, negative 1. And even though I only gave us one of those vertices, if I know where the center is, then the other vertex must be the same distance away on the other side. So negative 5, 2 is 3 units away from negative 5, negative 1. So I'll add 3 to the y value to get my other vertex. And same thing with my co-vertices. I'm given one of them at negative 1, 2. And so the other one must be the same distance away on the other side. So I'll count 1, 2, 3, 4 units, 1, 2, 3, 4 units away, and my other co-vertex must be right there. I will finish drawing my rectangle, and then draw the asymptotes in. And I suppose if all I really care about is what the equation is going to look like, I wouldn't need to draw the graph, but it's going to be helpful for me to visualize this. And frankly, it could be something that I ask you to do on a test. Negative 5, negative 1 is one of the vertices, and so the graph will actually go through this point, approaching the asymptotes, something like that. Same with the other vertex. Horizontal tangent when it goes through it, and then gradually approaches the behavior of the asymptotes as we get farther and farther away. Finishing up with the actual answer, because this graph is opening up and down, I will start with my y term, y minus the y coordinate of the center. It's 2 in this case, y minus 2 squared over something. I'll think about that later. And then I've got x minus, the x coordinate of the center is negative 5. X minus negative 5 is the same as x plus 5. So x plus 5 squared over something will be equal to 1. And then I look at the distances from the center. The vertex is 3 units away from the center. 3 squared is 9. And then finally, we'll have one that is not 9. The horizontal distance is 1, 2, 3, 4 units away, and so 4 squared is 16. That will be the denominator of that term. So there we go. Your homework will look similar to this, just going back and forth between different representations of hyperbolas, equations, graphs, all that good stuff. So good luck with that. Have a wonderful weekend, and we will check in again with you next week. We'll get you ready for the test that will be on Friday, and then we'll be done. Um, there we go. Have a great weekend, and I'll talk to you later. Bye bye.